respiratory epithelium is our pseudostratified columnar. Respiratory membrane is the sandwich on the diagram. And what you see up on the board, simple squamous epithelial sandwich. Okay. And then the reverse occurs when we have internal respiration. And internal respiration is gas exchange at the tissue level. We don't really have a membrane name for that, but it's across the capillary epithelium into tissue fluid. Or from, because it's both directions. And then of course we have cellular respiration, which we'll talk about with the digestive system, which is the use of oxygen in ATP synthesis, exactly, press cycle and electron transport. All right, so we're looking at, first of all, the gas exchange. Here, what drives out oxygen into the blood and a little bit of CO2 out. And we're going to finish up with discussing the affinity relationship between oxygen and the iron ion of hemoglobin and the oxygen dissociation curve. Tomorrow in lecture, we'll review that oxygen dissociation curve and talk about carbon dioxide. Okay? So let me diagram. This is our simple squamous epithelium, type 1. Our type 1 alveolar cell. Our type 2 alveolar cell is a component of the cell wall, but is not going to be involved in, has lipid droplets in it. It's going to be outside the respiratory membrane. But it's between, say, two simple squamous epithelia. And then we would have our capillary, which is also a simple squamous epithelium, and it comes very close to the simple squamous epithelium of the alveolus. This is a pulmonary capillary, and although I drew it in red, it is carrying the opposite type. We'll say this is the pulmonary capillary as it's leaving the lung. Because remember, what type of blood is it carrying into the lung? So the pulmonary arteries are coming into the lung and form arterioles, lose their smooth muscle, and form capillaries. Unlike the rest of the body, these pulmonary capillaries are going to be transporting deoxygenated blood. Right? And as they leave and form the veins, they will have picked up oxygen. Now the changes that I'm showing here take place over multiple alveoli. In other words, we're not going to completely saturate the hemoglobin of one red blood cell by just the blood flowing by one alveolus. It'll pick up some, and then it'll go by another alveolus, and another one, finally before it leaves the lung. Okay, for complete equilibration of gases. So again, this structure with the two epithelia, this would be our endothelial. Remember, endothelial cell is the simple squamous epithelium lining a blood vessel or forming the capillary. And this would be our respiratory membrane. All right, so oxygen diffuses into the blood via a concentration gradient. So it's going to move down its gradient. So we have more oxygen in the alveolus than we have in the blood. It's going to move into the blood. If we have more carbon dioxide in the blood than we have in the alveoli, carbon dioxide will move in the opposite direction. So the numbers up here talk about oxygen tension, partial pressure, and I'll explain those terms in just a moment. Alveolar oxygen pressure is given as PO2 equaling 104 millimeters of mercury for alveolar air. Okay. coming in from the heart, and it's venous blood, the PO2 is equal to 40.
What does the P stand for?
Partial pressure, I'll get to that in just a moment. It stands for partial pressure. So this is our gradient. This is why oxygen moves out of the alveolar air into the blood, because we have a gradient of 60 millimeters. By the time the blood leaves and goes back to the heart, the arterial PO2 is going to equal the same as the alveolar PO2. I'll come back and explain these terms in just a moment. Again, this doesn't take place at one alveolus, but by the time the blood is flowed by all the alveoli and is leaving the lungs, equilibration has occurred, and we have the same number of gas molecules dissolved in the plasma as we do in the alveolar air. Now, carbon dioxide is going in the different direction. So as it comes in from the heart, carbon dioxide has a partial pressure of 44 millimeters of mercury. It diffuses into the alveolar air because when that air that you breathed in, not expired air, but air that you breathed in, it's going to have a PO2, sorry, a PCO2 of only 40. Now that's not much of a difference considering the high gradient between oxygen and in the blood versus oxygen in the alveoli. But we'll talk about why it doesn't need to be as high to continue to get the air out. All right, so here on the next slide are a series of factors. This is just showing what's going on here. All right, so here's our alveolus. With ventilation, we're getting oxygen in and breathing carbon dioxide out. We don't take up all the oxygen. So when you breathe the air out, there's still going to be some oxygen, but a higher proportion of that is going to be CO2. All right, so let's look at what partial pressure means. Partial pressure has to do with a proportion. It's not that the gas itself is only partially there, but at any time we have a mixture of gases, all right, only part of the forces exerted by those gases moving around comes from one particular type of gas. So in air, may I erase these three terms over here? That was just really a review. You guys have that already multiple times, I believe. So when we look at air, it is a mixture of gases. The most common gas is nitrogen, okay? Or around 78 to 79% of air is nitrogen. Oxygen is not quite 21%, it's about 20.9%. And then we have other gases. Carbon dioxide is about 0.04%, I believe. And we have other components. Okay? Now, as we translate that to what it means by partial pressure, remember I diagrammed that tray of mercury when I was explaining millimeters of mercury? All right, so here's an illustration of that again. So atmospheric pressure at sea level is 760 millimeters of mercury, meaning that as all of the air molecules at sea level are pulled by gravity onto the surface of the mercury tray, it would push the line of mercury up to 760. If we took out all of the nitrogen, all of the oxygen, the nitrogen itself would only go that high. That's what 78% of 760 is. So each gas, depending on the number of molecules, is going to have its own contribution to the overall pressure. And that's what partial pressure means. It's particular contribution. Okay? It doesn't mean that it's partial, it's only part of its pressure, it's that part of the mixture of gases. All right? So if it was pure oxygen, then every single component of the pressure would be due to oxygen. Now, that proportion doesn't change. So if we take this tray of mercury to Death Valley, which is below sea level, all right, atmospheric pressure is going to be higher because there's a greater gravitational force pulling on so more air molecules are going to be pulled onto the surface, but it's still going to be almost 21% oxygen. It's not going to be higher, and it's not going to be lower. If we take this tray of mercury to 8,000 feet, there will be fewer gas particles at 8,000 feet, and so the overall pressure will be lower, but 21% of it, that pressure, if it's 500 millimeters of mercury instead of 760, 21% of that will be due to oxygen. Okay? So the proportion doesn't change, but the number of gas molecules in a given volume will change depending on elevation. So partial pressure, PCO2, PO2, is just referring to that gas's contribution to the mixture. Okay? And this is just another way of looking at it. Torr is another term instead of millimeters of mercury. So if oxygen has a pressure of, say, 200, nitrogen is 330, the sum of both of those gases in the same container would be that adding them together. So they still have the same force even though they're mixed up with another gas. Okay? Any questions on partial pressure? The term partial is confusing, but if you think of, you know, the subset of a mixture is really what we're talking about. Okay?
So if you're asking for a partial pressure for somewhere, you can give us a given amount?
I'd have to give you the total pressure and then the proportion, the percentage of that. So we neither increase nor decrease any gas's pressure by adding it to another. The gas itself. So if I have, you know, 25% oxygen and 75% nitrogen, that 25% oxygen mixed with the nitrogen still has the same pressure as if I had the same number of molecules all by themselves.
Right.
Okay? Yes.
Is that complicated when you add the water vapor? Because it says 5%.
Yes. Water vapor, and especially in the alveoli. Okay? So atmospheric pressure on a humid day is going to have a higher water atmosphere, and if we were pilots or we were other, you know, physics involved in that, we will look at that more closely. But water vapor in the alveoli is even higher than it is, as you can, it's more of a factor when we look at the overall change with carbon dioxide. Of a
Yeah, atmospheric 78, 21, 5%.
28 would be the 5. Maybe it's supposed to be a point. I'll double check on that value. Might be.
Oh, okay, 0.5.
But it's kind of interferes with the volume. So now here we look at the solubility in a fluid. All right. So gases will dissolve in a fluid, and that's Dalton's law. I'm sorry, that's Henry's law. Dalton's law is partial pressure. So Henry's law is at a constant temperature, the amount of a given type of volume and gas in a fluid is directly proportional to the partial pressure. All right, so if the partial pressure is greater, more of that gas is going to be soluble. So we have more nitrogen dissolved in our blood than we have actually oxygen. Because 78% nitrogen will cross the plasma membrane. It's not chemically active because it's a stable gas. It doesn't need any additional electrons. It doesn't need to give off electrons. So it doesn't chemically interact with our body. And so it only becomes a problem if you're a scuba diver and you're, you know, below 1 atmosphere for a longer period of time and the air that you're breathing is under pressure. Then if you rise too rapidly, you don't give a chance for that nitrogen to move into your lungs, then it starts to come out in the gas form and bubbles in your joints and in your blood and in your brain. So here, you know, unless you're scuba diving, that doesn't become a factor. Before I get to that, solubility across the plasma membrane is also a factor. So if we look here, notice the difference between carbon dioxide's gradient and oxygen's. We still get diffusion of carbon dioxide out because it is much more soluble across the plasma membrane. It moves more rapidly through the plasma lipid between the fatty acids, the phospholipids of the cell. So even though we don't need as high gradient to get an adequate movement, because it's going to move through here faster. So that overcomes the difference in gradient. Okay? Now, if the fluid is cold, well, you can look at that diagram. Is there a greater biomass in the Caribbean or the Arctic Ocean? Biomass meaning the total mass of living plants, animals, and all that kind of stuff. Arctic is correct because it has a greater, now it doesn't have the size or the beauty of the corals and the fish, but if you were to measure the plankton, okay, there's a greater total overall biomass because cold water has more oxygen in it. What happens if you have a pot of water and you boil it? You're adding energy to the gas particles and they come out of solution. Okay? Now, I don't know how many of you are pretend or obtaining to be Martha Stewart, but if you were going to hold a bridal party or a garden party this spring and you wanted to put nasturtiums or violets in the ice cubes, if you just go and freeze ice cubes, they're cloudy. You wouldn't be able to see the flowers. Okay? So how do you make clear ice cubes?
You boil the water.
You boil the water first, and that drives out the gases. Okay? Now you don't want to leave it at room temperature before you put it into the freezer because it's just going to take on oxygen from the room. If you put it in the freezer right away, of course then you're going to cook the flowers too, so you have to cool it down a little bit. But anyway, whenever you put it in plastic, then you get clearer ice because you don't have the gases dissolved in there. All right, so that brings us to this slide of Antarctic ice fish. And there's a whole order of fish. They live at temperatures. Seawater freezes at about -2. Because of the salt, it has a lower freezing temperature. That's why we put salt on roads. If it's snowy or icy, it lowers the freezing temperature. So they live between -2 and 4 degrees. So obviously that water is going to have a lot more oxygen in it than if they were swimming around the Caribbean. Okay? They have no hemoglobin. So their blood shows yellow, or plasma kind of color, instead of a red. And like us, we transport oxygen, as you'll see in a few moments, dissolved in the plasma. But they are limited. We would not be able to live if all we had was plasma. All right, most of the oxygen that we need is carried on the hemoglobin. You have anemia. What's some of the symptoms? Fatigue. You're tired. You don't have enough oxygen for your brain or your muscles to work. So because of that low oxygen, they demonstrate low metabolic rates. And they have some other changes that help them adapt. This is, their blood vessels are larger. So what does that do to flow? Increases flow because it decreases peripheral resistance. Isn't it cool how you know this stuff already now? There's a greater overall blood volume, greater cardiac output, low viscosity. Why is the viscosity low? They don't have any red blood cells, they don't have any hemoglobin. Okay, remember we talked about the ratio of fluid to red blood cells affecting viscosity? So with all of that, I know in the back you can't see this, they have a higher flow rate to pressure. So a more efficient movement of blood through the body. Now scientists at first thought they would get additional oxygen through the skin from the surrounding seawater. And that may help the heart because that blood's going to the heart first. Okay, but it doesn't seem to get to the rest of the tissues. They don't have coronary arteries. Instead, the heart muscle is spongy. It has vascular, kind of like sinuses. And so the oxygen diffuses directly from the chamber of the heart. Fish have only one ventricle. From the chamber of the heart out into the cardiac muscle. So it's real cool comparing those characteristics to what we already know about circulatory components and the need for the heart outflow. All right, so if we look at, obviously we can't change the temperature of our blood. Okay, I'm going to go run a track meet. I'm going to go sit in the freezer for a day so that I have extra oxygen in my blood while I'm running. It doesn't quite work that way, all right? Instead, if someone, say, needs a heart transplant or needs, the organ that they're using, they'll put in a cold solution to decrease the metabolic activity, slow down the use of oxygen, is usually the way. If someone drowns, especially children, cold water is better because, yes, it does have extra oxygen in it, but that's really not what's helping them. It's the effect of the cold on their own body's metabolic rate. And children seem to have a better chance surviving that. All right, so the partial pressure, what that means is the movement of oxygen across the membrane. And obviously we mentioned already that movement is going to be affected by the respiratory membrane thickness. So we have our normal thickness, which is just basically the thickness of the basement membrane and maybe a few strands of collagen fibers. And then we can affect that thickness by pathological conditions. So this first image here is showing pulmonary edema. So with pulmonary edema, we have high hydrostatic pressure in our pulmonary capillaries, and that obviously is going to not be resisted by the air pressure, and so fluid seeps across the respiratory membrane. Is pulmonary edema more likely in left-sided or right-sided congestive heart failure? Left-sided, exactly. So if the left ventricle is weaker, it moves, pressure backs up, blood flow is not moving the left ventricle. So it's going to back up into the left atrium, and then into the pulmonary veins, and then into the pulmonary capillaries, and eventually it would get to the right side of the heart. But while that pressure is high in the pulmonary capillaries, we get this seepage of fluid into alveoli. Okay, so obviously that's going to increase diffusion distance. Pulmonary fibrosis is shown over here, and you can see how much thicker the space is between alveoli. And that's due to additional, primarily collagen fibers, which has a much less, diffusion is going to occur much slower here than even through the fluid. You just wouldn't get as much air in the space of the fluid.
Yeah, what's causing fibrosis?
It could be a variety of diseases. There's a lot of it's idiopathic, where you have interstitial thickness. Who was it? Saw the name. Evel Knievel died of a form of idiopathic, unknown cause. But others can be industrial exposure. You would think, yeah. But if they can't trace it to any one particular cause, and I didn't recognize the comic Howard the Duck. Do you know that comic?
Oh, yeah.
The artist, author, whatever you call a comic writer, had something similar where they didn't know the cause of it. But it's usually industrial cause. Various forms of other respiratory diseases can lead to it as well. But most of the time it's one of those.
Here we go.
Okay, so obviously changing the thickness is going to affect that. So that would be changing this distance here. Also important, obviously, would be the overall surface area. Specifically, the overall surface area in contact with the blood vessel. Okay, a whole lot of surface area where there's no blood vessel is not going to do us much good. So if we lose alveoli, if alveoli collapse, all right, then we've lost surface area. If we lose blood vessels because of some damage to the lung, traumatic or whatever, usually you get both lots of blood vessels and alveoli, we're going to lose that relationship. Yes?
So if there's no respiratory membrane, if there's no blood vessel on the outside of that alveolus, just alveolus.
Right. So you would obviously, oxygen is going to diffuse into this tissue,
Right.
but it's not going to be transported anywhere.
Okay.
and it's lost to what might go into the blood. Okay? So anything that causes a collapse of alveoli or a loss of lung tissue is going to affect that surface area. And emphysema, I have listed there, that causes a rupture of alveoli. So remember we said compliance was easier. You had higher compliance with emphysema because it's the small little alveoli that tend to collapse and are difficult to stretch. With emphysema, we have large alveoli because there's a breakdown of the walls. So we don't have as much surface area, nor do we have the blood supply, and it takes longer for gas exchange. And it actually is difficult to move the air in and out, so we tend to have a higher CO2 as well because the gases aren't moving out. Okay, and then the last one is alveolar ventilation and perfusion coupling. So alveolar ventilation is the movement of air into and out of. Obviously, we need to bring fresh oxygen in, and we need to move carbon dioxide out. Perfusion refers to blood flow. So if there is a problem with blood flow, we can have adequate oxygenation, but we're not getting that oxygen into the tissues. And we'll talk about various forms of hypoxia when we talk about that. But what I want to focus on here is the paradox when we compare this to normal systemic tissues. So what happens if you're out running, okay, and you need extra additional oxygen to your thigh and close to your calf muscles? The arterioles that are supplying a bed of capillaries, would they dilate or constrict? They're going to dilate. So tissues that need oxygen release chemicals, the blood vessels themselves release nitric oxide, and relaxation of the smooth muscle occurs. If we switch to pulmonary capillaries, not bronchial, but pulmonary artery capillaries, and they're flowing by a region of alveoli which are not being ventilated. Let's say that there's a blockage, there's maybe that part of the lung is collapsed, there's fluid, pulmonary edema, and that cluster of alveoli, or pneumonia, and fluid in the alveoli was pneumonia. So as those capillaries flow by, they're not getting much oxygen. So what happens is the arterioles to that bed of capillaries will constrict and divert that blood flow to another segment of the lung that is getting ventilated. So in the body tissues again, when a tissue doesn't have much oxygen, the arterioles dilate, so capillaries carrying oxygen will flow to that area. In the lungs, when a segment of the lungs doesn't have enough oxygen, the arterioles will constrict because the capillaries are not carrying oxygen to that area, they're picking up oxygen. And so they will be diverted. There's no point wasting time having that blood flow through a section of the lung that's not going to be able to ventilate it, transfer oxygen. And so that will cause constriction of those arterioles. So you can see here when oxygen is low and carbon dioxide is high in the alveoli, this constricts and blood flow through that area is decreased. Right? If oxygen is high, then there's an even greater dilation and more blood flows through that area. That's essentially what's, and that's where the pulmonary vessels and capillaries. All right, so this is we're moving now to the next section, and those are factors that affected how gases move and what rate the gases moved across the lung, the respiratory membrane. Now we've actually got oxygen in the blood. What's going to happen to it? So it has, I'm going to keep this same diagram up here, but erase some of these